So our quick look at the calendar. Today we're finishing up quiz number 8 out of 10. We have a total of 3 topics left to cover before the next exam. Today we talk about complex numbers and polar coordinates. Next class we talk about vectors, and then we spend 2 classes on something called parametric equations. And then we have our review day, and then finally test number 3 is on April 30th, okay? So we're getting there. And one other thing, the project is due Monday. It's the project about music. Okay, so on page 24 of the packet is an introduction to complex numbers. Now, given that we just took a quiz, I think that what I had planned to do today was already too long, even if we had the full periods. So we're going to skip around a little bit, and I'm going to skip over stuff that I hope is easy so that we can do together the stuff that is more complicated. So I'm just going to point and ask you guys, do you know how to handle simplifying something like that? Yeah, so for some reason we don't like i's in the denominator, and so what you would do is multiply top and bottom by the conjugate, that's a good word, of the bottom. You put down there a 2 minus 3i, which is the same as what was on the bottom, but change that sign in the middle. But I need to multiply top by the same thing. So we're not going to do any more on this one, but I'm hoping that with a little bit of practice and a little bit of reading that you guys are able to simplify stuff like that. Raise your hand if you feel like you know how to do that already. What's that? It turns out that to get rid of something with an I in it, you need to multiply by the same thing but with the opposite sign. And if you multiply this out on the bottom, you will get 13. No i's anymore.
There was a snow day the day Linda was going to cover imaginary numbers.
Oh, okay. All right. Raise your hand if you missed imaginary numbers last semester. Okay. Imaginary numbers are numbers that involve this funny number I. I is defined to be the number that when you square it, you get -1. Now that equation just looks ridiculous, but it looks ridiculous because we have only been trained to think about the so-called real numbers. And in the real numbers, there is no number that when you square it, you can get -1. Well, we're going to introduce a symbol to define that number. The word imaginary is an unfortunate term because imaginary numbers are just as legitimate as the real numbers, but it's a term we are stuck with. And they behave just like x's. So for example, if I had 3 plus 4i and I wanted to subtract 2 minus 8i, I just treat those i's like they were x's, and you combine like terms in the ordinary way as if everything was, all those i's were x's. So what do you get when you do the real parts, the 3 and the subtract the 2? You get 1. And then we're doing the imaginary parts. 4i minus 8i is plus 12i. So that's how we subtract 2 complex numbers.
That means 12 times the number that equals when it's squared.
Correct. What does it equal? It is like a fundamental unit. I is something that you can't break it down into other stuff. It's as low as you can get. Well, I mean, it's like asking what does the number 5 equal? I mean, you can show me 5 things, but there is a concept known as fiveness, which describes the idea of having 5 things. So that.
I can picture 5 things. I can picture 12.
Can you picture -5 things? Can you picture -5/3 things? All right, I had more. Okay. Yeah, it's difficult. And in fact, if you aren't comfortable with this concept of I, this imaginary number, I cannot blame you. When these numbers were first thought about, I want to say something like 15th century, so not too long ago, a lot of people laughed the first discoverers out of the room and said, "You're crazy. There's no point in fiddling around with these things. It just doesn't exist. There's no number that you can square and get a negative." But people persevered, and eventually, it got some traction. So you can do arithmetic like we did here in purple. You can multiply complex numbers. In fact, let's go ahead and do this one out then. So multiplying complex numbers means using FOIL or distributing. So go ahead and distribute upstairs and distribute downstairs. The eyes on the bottom will just drop. Upstairs, you'll still have eyes. Did they go away up on top? I think we should have them. Let's see. 2 minus 3i plus 4i minus 6i squared. Any questions about the foiling upstairs or downstairs? Again, if I is too much to look at, put an X there. It behaves the same. And then let's clean things up. Let's see, in the middle, how many I's do you have? There's a plus 1i upstairs. There's a 2 plus an I, and then there's something else, that minus 6i squared. I'm going to leave that for just a second. Downstairs, what happens with the i's? They cancel. That was kind of the goal, actually. So 4 minus 9, and then something. But if you see an I squared, what's our fundamental definition? It's -1. So you are obligated to replace every I squared with a -1. And so on the bottom, you really have 2 plus 6. Sorry, that's the top. 8 plus I is upstairs. And on the bottom, 13. 4 plus 9 is 13. Questions on that? Do we see why multiplying by 2 minus 3i is a good idea if you don't like i's in the bottom? Right? That's the thing that's going to get rid of the i's, because that's the thing where the outers and inners will cancel. That minus 6i and plus 6i disappeared. Okay, technically, we're supposed to write our numbers in the form a plus b times I. That's the goal. Okay, I'm going to make this 2 fractions. The first fraction is what? 8/13. That's 1 fraction. Plus the second fraction, it is I over 13. I'm going to write the I on the side. It's 1/13. So make sure you see that those are the same. 13 in the bottom can give you 2 fractions. 8 over 13, and then I over 13. But again, the goal was a plus bi, so I really like to pull that I out to the end. Questions so far? Okay, take your calculator out, and let's play around with a new button on the calculator. What I'd like to do is ask the calculator to do this division, the original problem. So we're going to type in 1 plus 2i over 2 plus 3i. But what do we need to type as the first symbol? Parentheses, because the whole numerator needs its own parentheses. Same thing downstairs. 1 plus 2. Anybody see the I character, the I symbol? There's a capital green I above the x squared, but that's not what you want. Vanessa, where is it? It's in the bottom, right above the decimal point. You see the fancy I? Boy. And we're going to get some crazy looking decimals. But guess what fraction is equal to 0.6153, blah, blah, blah. That's going to be 8/13. You don't have to take my word for it. How do you get the calculator to convert decimals to fractions? It's inside of math. Very first option is fraction. Enter, enter. 8/13 plus 1/13 I. Good. Calculator can handle complex arithmetic.
Why does getting it?
Yeah, so the A plus, are you asking why that's better than the first one?
Yeah, I guess.
Yeah. Okay, so in the same way that we all have this convention that, for example, you would never leave something as 3/6, you would just make it 1/2. We want everybody in the world to ultimately say the same thing. And it turns out there's a lot of ways to say 1/2, but I'd really like you to write it as 1/2 instead of any of the other ways. There are a lot of ways to say 8/13 plus 1/13 I, but let's all be uniform and have a goal in mind that we call like the simplified way to write a complex number.
What is the idea that you're isolating the imaginary number as much as possible?
Maybe that's one of the goals. I don't know. All I can tell you is that you could have written 8/13 plus 1/13 I as that fraction, and there are a lot of other ways you could write it too. Somebody has decided this is the way to really tease them apart, and maybe it's because they wanted the I part off on the side. Okay, let's go down to we're going to skip. Well, all right, let's just do 3. It's quick. Ernie. Okay, and so the conjugate of a plus bi is just a minus bi. That was the thing we multiplied top and bottom by. And it's denoted by that little bar over the number. So for example, what did we have? Was it 2 plus 3i? Is that on the bottom? If you put a bar over it, that's our way of saying do the conjugate, 2 minus 3i. Silly notation. I don't think we'll ever use it again. Vanessa, number 4. All right, so on the left-hand side, it looks like the xy plane. It's not. This is the imaginary plane, or the complex plane. You've got a horizontal axis, which is no longer called x. It is called the real axis. And then a vertical axis, which is no longer y. It's the imaginary axis. And so if I ask you to plot the point a plus bi, you're going to go a on the real axis and b on the imaginary axis and put a point. And so for example, down here, it says plot 3 plus 2i. So that 3, it's kind of like the x. And that 2 is kind of like the y. So really you're plotting the point 3, 2. That right there is 3 plus 2i. We are recording. Good question. Okay, go ahead and plot these other 2 points, -5 minus 3i and I. Any questions about plotting points? Okay, it turns out that we don't always want to write our numbers in the form a plus bi. Maybe sometimes we want to write them in terms of polar coordinates. Instead of describing to me to get from the origin over to -5 minus 3i, instead of saying walk 5 left and 3 down, what if you said, oh, you're supposed to walk this far, like a straight line this far, and you're supposed to do it at a certain angle. This is what we covered last time, right? So it's the same, it's the same x and y as it was before, so it's the same formulas as it was before. Can you guys fill in those formulas? How many of them do you remember? First 2 equations should have x's and y's. Second 2 equations should have r's and thetas. Okay, so we have the same 4 equations that we had from before. So what we're going to do on the next page is actually find out how long that purple line is. That's the straight line distance. And we're also going to find out what the angle is. I'll call it theta. Before we do, can we just make a guess? Just ballpark. How long is r? Don't do any calculating, just kind of count boxes, but it's tough because it's at an angle. And then what angle are we writing? Just write down, commit to something. How far is it if you had to walk a straight line? And what angle is it? Okay, how much is r? 6, 7, split the difference. 6.5, something around there. And then how about the angle? 1 vote for 210? Sure, something like that. Something around that, right? Okay, let's use our formulas to actually find what we get when we convert. This is what a question might look like on a quiz or test. Convert -5 minus 3i, that's the point, into polar. So we're going to use our formulas. We know that r is the square root of x squared plus y squared. -5 squared plus -3 squared. No, the I doesn't go in. This is supposed to look like an x plus y times I, like a plus bi. And let's say to the nearest 10th, what is the square root of 34? 5.8, good. Our guess of 6 was quite good. And then the theta is the inverse tan of, always put the y on top. Which one goes on top? -3 divided by -5. Okay, with the calculator, how much? 31 degrees. Yeah, does 31 degrees make sense? I'm not denying that Todd has typed that into the calculator correctly, but does 31 degrees make sense for the angle in green? No. Yeah, the angle in green is the calculator's way of saying, well, okay, I can do inverse tan, and I'm going to give you an angle that's in the first quadrant if the number is positive. -3 over -5 is positive. It's always going to give you something in the first quadrant. Turns out that was around 31 degrees. So really, it's 180 plus that is the true answer. So 211. But we're good at guessing today. And then we'll add our 180. Could you give me to the nearest 10th actually, Todd? What was that? Oh, it still rounds to 31? 31.96? Okay. 31. Okay. This one actually doesn't, we're going to write it. We don't have a way to write the 5.8 and the 211 other than, like the point is 5.8 and 211, just like we wrote r and theta last class. But we're going to come up with a way to write this without commas, without an ordered pair. So we're going to do that here in 8. And let me warn you that things are about to get notationally kind of heavy, and it's just going to be a lot of new symbols. But be patient. The symbols will start to sink in with a little bit of time. We'll go to Hillary for number 8. Let's pause there. Everybody buy it? Because we know that x is our cosine theta, right? All right, so we just replaced. Keep going, Hillary. What did we do there? Just factor out the r. Hillary?
Two symbols.
Okay, so it's read r cis theta, like literally like SISS, if I could write how I'm saying it, r cis theta. And what does it stand for? Well, that r is this r sitting in the front. What is the c? C is cosine. What is the I? The I is, it's I. What's the S? Is sine. So we are really crunching symbols down. It's like when they like encode information and try to smush it into like as small a little packet as possible on computers. Like that's what we've done here. So r cosine theta plus I sine theta is now r cis theta. It's just smushed down. But the r and the theta are the same ones that we just got up above. So if we wanted to use our new abbreviation to write -5 minus 3i, I'll write it longhand first and then shorthand. It turned out that this was really r times, what was the r? It's 5.8 times the cosine of, what was the angle? It was 211 plus I sine of the angle, 211. Now it might look mysterious, but if you just type that thing into the calculator, you'll get the right answer. If you type in 5.8 cosine 211, you're going to get something really close to -5. It just is. You just type it in. It's all you found. And if you type in 5.8 sine of 211, you'll get something really close to the -3. The I is a placeholder. It's just still sitting there. But we don't want to write all those symbols, so we really smush it down. And we're writing it as r cis theta. What was r? 5.8. Cis is a new symbol, which means a lot. Theta is 211. 5.8 cis 211. There's no cis button, but we're going to get a button on the calculator we'll use in a second that will be close. Close, close. Okay, number 9, Garrett.
Why is this deliver a result called loose formula?
Okay, so maybe we've heard of Euler before. It looks like Euler, but it's pronounced Euler. Euler is one of the most prolific, maybe number 1 or number 2 most prolific mathematicians of all time. He was from Switzerland, lived 18th century, and lived for a long time, like 75 years or something, and just wrote and wrote and wrote and wrote like volumes of math and science and all good stuff. And here's one of the many things that he did. Do you guys remember, I think on the very first day of this class that we looked at up on the board was a bunch of like 3-dimensional solids that you had to count the number of vertices and count the number of faces and count the number of edges. Did we do that? We did that in this class. Yeah, and you guys came up with some formula based on all the information that said that if you took the number of vertices and subtracted the number of edges and add the number of faces, it was always the same number for all the different, like a cube or a pyramid or an octahedron. Anybody remember the magic number? You don't remember what happened before the first day of this class? It was always 2. And that's one of Euler's many contributions, is that formula. Okay, here's another one. E to the I theta is equal to cosine theta plus I sine of theta. All right, if you don't buy into this whole I idea, then good God, what does it even mean to take E and raise it to an imaginary number times some angle? Okay, well, it turns out Euler was able to kind of give meaning to that symbol, E to the I theta. He said, look, it's just cosine of theta plus I sine of theta. That's what it is. And we're not going to prove this theorem. We're not going to really even talk about what it means to take E and raise it to something imaginary. We're just going to accept it. So here's what I want you to do. I want you to use that formula and tell me what is the value of E to the pi I, or if you prefer, E to the I pi. Can you use that formula? Check with your neighbors. Use that formula to find what is E to the I pi, really.
cosine pi is sine 0.
-1.
So what do we get? -1. E to the I times pi is -1. Okay. So if I decided to add 1 to both sides, what do we get over here? We get 0, right? Just by adding 1 to both sides. Okay, I'm going to highlight this. We're never going to talk about that equation again, but many argue that this is the most amazing equation in all of mathematics. It relates E, that number which has to do with exponential growth. It relates I, these imaginary numbers. It relates pi, which has to do with circles. It relates 1, which is the multiplicative identity, and it relates 0, which is the additive identity, all in one beautiful equation. With an equal sign. With an equal sign. Okay, so after class we can debate what you can tell me what your most favorite equation is, but that's a lot of people's favorite equation right there. All right, let's use Euler's formula here. One other version of Euler's formula says that if you have an r in the front, r cis theta, then that's the same as an r in the front of e to the I theta. Do we buy that? That's, I mean, if we believe that e to the I theta is cis theta, then stick an r in front of both sides and we get r cis theta equals r e to the I theta, okay? Just symbols. I told you, I warned you it was going to get notationally heavy. Yeah, so the two green things up above are, it's Euler's formula. It says e to the I theta is cis theta. That's an equation that we're going to buy right now. Just stick an r in front of both sides by multiplying both sides by r. And we get r cis theta is the same as r e to the I theta. Okay, so then let's come down here to our favorite -5 minus 3i again. -5 minus 3i. What did we decide this was equal to up above? -5 minus 3i was really equal to 5.8 cis to 11, right? That's what we wrote up above. How we're going to write this in a slightly different way. Our new favorite version of complex numbers is r e to the I theta. What's r? Still 5.8. E is E, I is I. What is theta? 211. Let's go ahead and put the I at the end. So that's, yeah, that's using this version of things. If you have r cis theta, that's the same as r e to the I theta. But yeah, either way, normally you put the number in front of the I, but it doesn't matter. It's multiplication. We should be in radians the whole time, but we're just going to do degrees. Okay. So Ali had asked about a button on the calculator, so let's get those calculators back out. Let's see if we can do anything here. Okay, so what's going on? Let's see. So I'm going to type in that -5 minus 3i, -5. Oh, wait. First I want to type in this craziness over here. E to the pi I. Second, e to the pi I. What did we say this was equal to? We said that was -1. According to Euler's formula, does the calculator know what to do with i's above e? You bet. So just for kicks, e to the 2 pi I. 2 pi I. It's not I. It's not -2. It's 1. It's that previous. Yeah. Because back over here, instead of putting pi's, we should have put 2 pi's. Cosine of 2 pi is how much? It's 1. Sine of 2 pi, 0. So the whole thing is just 1. So when I went to this this Rubik's Cube tournament back in 2009, they made up shirts and they said, well, what number would you like? I said, I said e to the 2 pi I. Give me number 1.
Your fancy report.
You know, a lot of people in the audience actually knew what this meant, so we were okay. We were okay. All right, so and it's probably pretty wrinkled. It's been in my drawer for roughly 1 year, so. All right, so let's go back here. -5 minus 3i. So that was our favorite number we've been playing around with. And I mean, if I just hit enter, I don't think the calculator will do anything. It'll just tell me, okay, -5 minus 3i. But suppose that we do this. Suppose that we do something. Suppose that we do this 5.8e to the 211 stuff. 5.8 e to the 211i. What should it say? What does that equal to according to all the stuff that we did? That's what we're saying. Like I'm telling you, these guys are equal. That 5.8 e to the 211i is equal to, it's another way to say -5 minus 3i. Now, I have a bad feeling about this. Did it work? Wait. Oh, it did. Yeah, I mean 5.8 was not quite the right number. But look, -5, and you keep scrolling over, and -3. And if you keep going, what will you find at the end? I. Okay, so it's telling me, going from the 1 back here, it's fine. But suppose we wanted to go the other direction. Suppose you had -5 minus 3i, and you didn't want to do all that work, all the converting work, in order to get the 5.8 and the 211. So if you go into mode, and you go all the way to the bottom, almost all the way to the bottom, and you change the thing that says real to re to the theta I, which now we kind of have a sense of what's going on there. That's our new notation, this re to the I times theta. So if we change it to that, and then I just ask it again to tell me what is -5 minus 3i. Right, so my bad feeling was unfounded last time. I'm hoping it works here. I don't know. I feel like something isn't going to work. Is this going to work? I'm hoping it tells me 5.8 e to the 211. Okay, the 5.8, that looks familiar. And in fact, that was the number you guys got before, like unrounded. Okay, e to the, I was hoping for 211. What does it say? -2.6. I am in radian mode. All right, let's change it. And I'm just going to hit enter again. And it says -149. Is 211 the same as 149? Yes, it is. Good. Okay. So as long as you're in degree mode, it will give you the right degree answer. So calculator, so Ali asked if there was a sys button. No, but there is a way to ask the calculator to go from a plus bi to the re to the I theta.
So what's the restriction on that? Is that between like 0?
Yeah, it's a good question. Why did it give me -149 instead of 211? I have not played around with this mode very much, so I don't know what the restriction is, but maybe you could type in a bunch of numbers and try to come up with the range. Yeah, it's a good question. Okay, let's go to number. I'm going to skip 12, jump down to 13. Chris. Okay, do you guys have a way to do this, ignoring all the stuff from today? A very long way to do this. Do we see the very long way to do this? -5 minus 3i, -5 minus 3i, FOIL, and then bigger, 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 lots of stuff, and then condense. Okay, here's the better way. First, we have another way to write -5 minus 3i. We said this was the same as, what was it? 5.8 e to the 211i. Still raised to the what? 6. So numbers in the parentheses are equal. Just two different ways to write the same number. But aha, we have nice ways to deal with exponents on things like this. In some sense, I can distribute the 5.8 into the parentheses. It's 5.8 to the 6th times e to the 211I to the 6th. Agree? Exponents outside of multiplication work really well. All right, 5.8 to the 6th is easy enough to find, although since you're using your calculator, maybe you could go back to the unrounded version of 5.8 just to be as accurate as we can be. But then on the next piece, 5.8 to the 6th times, what do you do with these things, like the 6 and the 211? We multiply them. We have a rule about, like, this has nothing to do with i's. This is just an exponent property. You get to multiply things when they look like that. So this is really e to the 1266 I. I did not. Well, 6 times 2 is 12. Okay, so in theory, we're done. You just have to type in the 5.8 to the 6th on the calculator, and you've got it. However, the original answer looked like an a plus bi, right? Like this. And it would be kind of strange, like we've gone to this other equivalent world, but it doesn't look like a plus bi anymore. So it feels like we should bring it back to a plus bi. All right, so then what does it mean to bring it back? So I've got 5.8 to the 6th, which we're still going to hold on to. And then e to the 1266I, well, that was the same as cis of theta, right? That right there is really cis of 1266. This was one of our lots of notationally heavy stuff. One of our equations is the e to the 1266I is just cis 1266. And then what does cis really mean? It means cosine of 1266 plus I sine of 1266. So we're kind of expanding it so we can type it into the calculator. And now I can type it into the calculator. Okay, so the 5.8 would probably should do better than that. So let's do better. Yeah, you guys got that 5.8 from the square root of 34. So that's my 5.8 number. I'm raising it to what? To the 6th. So we get that. Oh, interesting. Guys, it's a whole number. Right? If I do any of the rounded stuff, it won't be a whole number. Am I surprised it's a whole number? Not particularly. If you had done this the really long way where you expand it all out, everything would have been nice numbers, right? Wouldn't have gotten any fractions at any point. Okay, so as long as you use the calculator to its fullest, you'll get the right answer. So that's 39,304, that's fine. So this is 39,304 times, and then we got to do these two pieces, the cosine of the angle and then the sine of the angle. But again, I'm gonna go back. So we did an inverse tan of what was it, 5/3? No, 3/5. Okay, so that was our 31, but that wasn't really the angle. Plus 180, that's really the angle. Okay, so that was my 211. I'm going to go ahead and store that as x just because I'm going to use it twice. Oh, probably I should do something else to it first. What do we need to do to it? Times it by 6, right? We wanted this times 6 version of that number. So let's times it by 6. All right, so 1265, that's good. So that one I'll store as x. And I just need cosine of that. and I need sine of that, and then we're just about done. Okay, so I'm going to write down those things. I'm going to round them a little bit here, but then we're going to go back to the calculator and use all those digits that it has. So what we just figured out was that cosine of 1266 was 0.994. That one was negative. Oh, negative, thank you. Minus, and then there's an I, and then the sine of 1266 was 1.007. Is that right? Oh, it was just 1007. They were both negative. Yeah. Okay, so that's those two numbers over there. And then in the front of all of them, what did we have? Was this 39304? So let's do 39304 times the cosine of that guy, and we get that. And then 39304 times the sine. We get that. Again, I'm not surprised they're nice numbers. If we had done it the long way, at no point would we have gotten any not nice numbers. They just would have been a lot of calculations. Okay, somebody help me remember those numbers. So we get negative 39.104 minus 3960. There we go. Yeah. So there were a lot of calculator details there, but none of it was hard, I don't think. It was just a matter of storing numbers in the calculator.
So the real reason you're going to the purple, so you can graph that.
So that you could graph it, certainly.
So that gives it meaning.
Yeah, it's easy to graph if it's like that. I'll buy that.
There has to be a purpose to doing all of that.
You could also have graphed it from here. Well, let's go back from here, 5.8 to the 6th, and then at an angle of 1266 degrees will land you on the same point. It's just telling you how far to walk from the origin at an angle of 1266 degrees. And I claim that that's a whole lot less work than actually doing out all this big multiplication, 6 of them. Imagine there were 600. It was to the 600th power. Yeah. Is this any harder if it's to the 600th power? No. There's just punching stuff into the calculator. Okay, so I'm just curious now. The original thing was -3 minus 5i? No, that's backwards. Okay, so I'm just curious to see if Wolfram Alpha can handle this guy to the 6th. Okay, there you go. Is that what we got? Yeah. So I'm curious. I wonder if that's how it does it. If it does it the way that we did it, or if it actually multiplied it out. Because for a computer to multiply that thing to the 6th does not take very long without any shortcuts. Is that 39304? Is that something we've seen? Right, we saw that was the radius. Then we see this negative 174 degrees. 1211 degrees, but we didn't actually figure out what it was. Can you bring 1211 back to something between 0 and 360? So we had 1211 degrees. If you subtract a few 360s, what do we get? So I get to 851, and then 491, and then 131. And if we do one more, oh, thank you. Subtract 360. Okay, so I subtract a bunch of 360s, so it's really 186 degrees. It's the same as the 1266. For some reason, They said minus 174. I buy it. It's interesting. It was the same thing the calculator did. It gave us the, some negative thing. So maybe there's some standard way to write those angles. Okay, so that is that. Good, good. And then the other thing I can ask the calculator to do is, again, going back to the beginning, -5 minus 3i. And we raised it to what power? 6th. And I got that. Did you get that? I got this same thing Wolfram Alpha gave us, same thing we found by hand. If I wanted it to give me the other version, this -39104 minus 3960i, could I get the calculator to do that instead of giving me this r e to the I theta? Yeah, it's giving me what I asked for. And here in the mode, if I ask it for a plus bi, I'm going to leave it in real version. It'll still give me the same thing. It only gave me the r and the theta because I asked for it. But if I just hit enter right now, it gives me the a plus bi version of things. Okay, so here's what I'm thinking. At the very end of this semester, the last day of class, it says TBA. That was in case we had a snow day, which we didn't, and it feels like we're not going to. So how about we're going to kind of let this section spill over a little bit into next class because there's this big old group activity I'd like you to do, but certainly there's not near enough time to do it right now. So why don't we spend the last 7-8 minutes of today just doing this. When we come back next class, we're going to do together number 14. Part of the group activity at the end of the group activity involves this technique. Some of the homework questions involve that technique. I'll say do as much of the homework as you can for right now, but I'm not going to collect anything next time. We'll just make it due the following class. And then we'll give you maybe another 20 minutes next class to keep working through this thing. Okay? So like maybe half of next class, we'll just kind of finish up this, and then we'll start the next class, and we'll kind of be in between for a little bit. Eventually, we'll end up taking up a full extra day. And if you're okay with that, then so am I. Can you guys see what you can do just as far as you can get here, and then we'll just pick up there next time.